Okay, class, thank you for watching this video today. Today we're going to be talking about integral transformations or integral transforms. And these are a lot like the Fourier series that we talked about last time. There's going to be a few minor differences, and for the most part, we're going to be talking about Fourier transforms today. And at the end, we're going to go into a little bit about other types of integral transforms. So please bear with me, and hopefully we can get alert here. So in order to understand the Fourier transforms, the thing you want to start with is a basic Fourier series. So with the Fourier series, we've got, for example, f of t is equal to the sum from over n from negative infinity to infinity. And you have, I'm going to use the exponential form, c sub n, and then an exponential of 2 pi I n t over some big T. This can be simplified a little bit, and we can just write it as a sum over n of c sub n e to the I omega sub n of t, where omega sub n is just simply the frequency. And so we can think of that as 2 pi n over t. And so we also have this coefficient c sub n, and we can find the coefficient by just simply integrating um, over, 1 over t and integrating from minus t over 2 to t over 2. And, we're just integrating this function f of t with e to the minus uh, I omega n t dt. So you can see we have the Fourier series, and we have this other term, which is basically just finding the coefficient. Now, one thing is that we can also think about this finding this coefficient in terms of what we're going to call the delta of omega. And the delta of omega is basically how omega changes as you go from, say, n equals 1 to n equals 2. And that's just simply could be defined as 2 pi over t. Because every time you go from, as n, the integer n gets 1 higher, what's happening is we're just adding another 2 pi over t to it. So we can also use that in our definition, and we can rewrite this as delta omega over 2 pi times this integral from minus t over 2 to t over 2. And then we're just integrating f of t again as usual, and e to the minus I omega n t dt. So you can see here again, this is again just the basic Fourier series that we talked about last time. Now what we're going to do is we're going to take this a step further, and we're also going to rewrite our function f of t to be equal to this summation over n of the c sub n, and the c sub n we can write as delta omega over 2 pi times this integral from minus t over 2 to t over 2 of some other function, let's say f of u, where u is just something that's not equal to t, e to the minus I omega sub u times u du, and then all this times e to the I omega sub n t. And what you could see here is that everything from here over to here is basically just c sub n. So effectively, this is the same thing as just saying we're going to have f of t as c sub n and then this other stuff. Now what we can do with this is we can look at certain extremes. So if we take t to infinity, as t goes to infinity, since the definition of omega of the delta omega is 2 pi over t, then as t goes to infinity, delta omega is going to go to 0. And we can also define this new function g of omega to be equal to t times c sub n. And so what we're effectively doing is we're taking a limit as t goes to infinity, delta omega is going to drop to 0 naturally, but this transformation should not necessarily go to 0 because f of t doesn't go to 0. So in a sense, in general, we can look at these limits as when you take a summation of, say, f sub n, where f is just something parameterized by n, and you take that limit, then what happens is this sum can become an integral from minus infinity to infinity of f sub n dn, where what we're doing is we're saying that all the n's are so close together that instead of them being discrete, they're actually just becoming continuous. And then that, in turn, could be t over 2 pi times the integral from minus infinity to infinity of f of omega d omega, where I use the definition of omega in order to replace the delta in the n with the delta in the omega. So in this case, dn is equal to t over 2 pi d omega. And also, we can say that f of some function, like say omega, is equal to f sub n. So therefore, we can say that f of t, using this same limit, can actually become 1 over 2 pi times the integral from minus infinity to infinity of d omega. Sorry, that should be an omega, times the exponential of I omega t times the integral from minus infinity to infinity of du f of u e to the minus I omega sub u of u. And so you could see here that all we really did was we took the original summation and integral, and we took this original summation and we basically turned it into an integral. So instead of just being a sum over n, we're now this integral over d omega. And you could see that this follows from exactly what happened before. So we can also look at our function g of omega that we defined earlier. Oops. And g of omega is equal to the integral from minus infinity to infinity of dt f of t e to the minus I omega t. And that came about because remember we had originally defined this as being equal to t times c sub n. And so effectively what happened was when we define c sub n in terms of that integral, then this is just the natural result. And f of t, meanwhile, is defined as 1 over 2 pi times the integral from minus infinity to infinity of d omega of g of omega e to the I omega t. And what we did here was we basically just replaced the f of u with this g of omega. So it's effectively the same thing. It's just just rewritten using a different variable. And you could see from this that f of t should just be equal to 1 over 2 pi times the integral from minus infinity to infinity of d omega times the integral from minus infinity to infinity of dt prime f of t prime e to the I omega t minus t prime. So all I did here was I just combined the two exponential terms, so we just had one to deal with. And since f of t should be the same as f of t prime, if t prime is equal to t, then this is the same thing as saying that we're just integrating from minus infinity to infinity dt prime of f of t prime times a delta function t minus t prime. And what this delta function does effectively is if t is equal to t prime, it's a 1. If not, it's a 0. So delta of t minus t prime is really equal to 1 over 2 pi times the integral from minus infinity to infinity of d omega e to the I omega t minus t prime. So all I did was just comparing the equations, and you can see that very clearly. Now, another thing I should point out is that sometimes these Fourier transforms and inverse transforms are written where instead of having the 1 over 2 pi on the what we call the inverse transform and nothing, no constants in front of the transform, sometimes they'll put a 1 over square root of 2 pi over both of these. And so that just makes everything look more symmetric. So I want to do an example here using a Gaussian. And, Gaussians are good because with the Gaussian, it's basically something that we would use in a lot of situations just to show that something follows some kind of normal distribution. So they show up in classical mechanics and statistical mechanics and quantum mechanics and pretty much everywhere else. So let's say we have our f of t, and it is equal to 1 over tau square root of 2 pi times the exponential of minus t squared over 2 times tau squared. And this t exists from a range of negative infinity all the way up to positive infinity. So it covers all of space. So you can see that as t goes to negative infinity or positive infinity, because of the exponential term, it's going to basically fade away to 0. But around t equals 0, it's going to hit a maximum. So it's going to have just kind of this, it's going to have a curve kind of like this, so centered around 0. And that's just a Gaussian distribution. And so what we're going to do is we're going to actually take the Fourier transform of this Gaussian distribution. So what I'm going to do is I'm going to say the Fourier transform of this thing, and I'm going to use this little twiddle to represent any time we have a Fourier transform or a transform, is going to be 1 over square root of 2 pi from here, or from, just the general transform equation, from integrating from minus infinity to infinity of f of t times e to the minus I omega t. Oops, it should be omega dt. Now, this is just the general equation to start with. So what we're going to do is we're going to plug in our Gaussian, into that. And so we end up with 1 over 2 pi times this integral from minus infinity to infinity of 1 over tau times e to the minus t squared over 2 tau squared times e to the minus I omega t dt. And so all you really have to do is solve this integral and you're done. But unfortunately, this is just not a really simple integral to solve. The way you would solve it is you're going to use, I know last week we used integration by parts, which you guys probably hadn't seen in a while. This time we're going to use completing the square. And the idea is if we can complete the square, then we can show how to solve this integral really easily. I don't think that the book goes into much detail on this, but I will for you guys. So we have minus t squared over 2 tau squared minus I omega t. The way I got that was I just looked at the terms in the exponential. So you could see that here we have one term, and here we have another term. And if you put those together, this is just the stuff in the exponential. What we're trying to do is we're trying to get this as just the square of something, much simpler. So I can take this and I can pull out a common term. And so I have 1 over 2 tau squared times t squared plus I times 2 tau squared omega t, which comes from, the second term. So if you multiply all that together, these two sides should be equal. Now, what I can do with this is if I add and subtract an extra term in here, this could actually look like the square of something. So I know I have the t squared. I have another term here involving a t, and so that looks like that's kind of the middle term. So I have I 2 tau squared omega t. Oops. And so what I'm going to do is if I put in another term that looks like tau to the 4th omega squared, that looks kind of like if I took the I tau squared omega and I squared it. And by squaring it, I end up getting a negative sign, and I get the tau to the 4th and the omega. But in order to add that term, or subtract that term, I need to add in the equivalent term. So basically, I added in 0. So these two terms added together give me 0. But if I ignore this last term, then all this other stuff is basically just one thing squared. So I can think of this as minus 1 over 2 tau squared. And then I take these three terms, and that's just going to be t plus I tau squared omega squared. And then I have this last term, which is going to be equal to minus 1 over 2 tau squared times tau to the 4th omega squared. And then I could just divide out the tau to the 4th, or tau squared from tau to the 4th, and that simplifies a little bit. So the net result is I have one term here, which is a perfect square. It's just going to be t plus I tau squared omega squared. And then I have another term here, which is just basically a constant, because tau is a constant and omega is a constant. So that's just a constant. And with constant terms, I could pull them out of the integral. So now I can rewrite my my Fourier transform of omega as being equal to 1 over 2 pi times tau times the integral from minus infinity to infinity of the exponential of minus 1 over 2 tau squared times t plus I tau squared omega squared times another exponential involving that extra term I had, which is just minus tau squared omega squared divided by 2. And I'm integrating all that over dt. Okay, so this last term I could easily pull out of the integral. And when I do, I'm just integrating this term involving the exponential involving this stuff with the t squared. So what I want to do is I want to make a change of variables. I'm going to create a new variable u, where u is going to be t plus I tau squared omega. And du, conveniently, is just going to be dt. So when I put in these new variables, I can change my Fourier transform in terms of that new variable, which I'm integrating over anyway. And so I have 1 over 2 pi tau from this first term. Then I have this exponential term, e to the minus tau squared omega squared over 2. And then I have this integral where it's basically going to be e to the minus u squared divided by 2 tau squared du. So that should be squared. And so you can see here that this is a very simple integral now. And I know from Shalom's outlines that if I integrate from minus infinity to infinity, and by the way, you can still see that the limits are still minus infinity to infinity, because as t goes to infinity, u goes to infinity, and vice versa. So I know if I integrate e to the minus ax squared dx, the result is going to be square root of pi over 2, or sorry, over a. Then from that, I can see that f of omega should be, I put in the constants, I have the exponential constant, And then the solution to this integral is just going to be literally square root of 2 tau squared times pi. And the reason why you can see that there's a, because this term in the denominator is basically 1 over a. Now, this can be simplified further because you can see that we can have the tau can come out of here, out of the radical, and you have a 2 pi, square root of 2 pi and a 2 pi. So this whole thing can simplify down to 1 over square root of 2 pi times the exponential of minus tau squared omega squared over 2. And this is also a Gaussian. But the difference is the width of this Gaussian is 1 over tau, where the width of the other Gaussian that I was dealing with earlier was just tau. So they're basically equivalent. Let me show you the original function that I was dealing with. Was given as 1 over square root of 2 pi tau e to the minus t squared over 2 tau squared. So if you compare these two formulas, they look very, very similar. Like I said, the only difference is that the width is inverted. Now, the fact that the width is inverted is really interesting to us in physics because of something called the uncertainty principle. You'll notice here that if you take the delta and omega and you multiply it by the delta and t, they're going to be roughly equal to 1. And the reason why is because if the original function f of t looks like this, or this is t, then the width here is given by tau. But meanwhile, if you look at the Gaussian distribution we get at a Fourier transform, this is going to be f twiddle of omega. And you can see that this is omega here. The width here is going to be 1 over tau. So as you make the first one wider, the second one gets more narrow. And if the second one gets more narrow, the first one gets wider. So this width between the two, we can think of this width as the delta of t. We can think of this width as the delta in omega. And if you multiply them together, they're basically a constant. And so they have inverse widths. This is very similar to the uncertainty principle, which is basically saying that delta p delta x is equal to h bar over 2, which is a constant. And so this is the Heisenberg uncertainty principle in just very simple terms. All right, the next thing I want to talk about is the Dirac delta function. Now, the Dirac delta function is a little bit different than what we've dealt with before. Here, it's a function where if we take the delta function of t, it's going to be 0 if t is not equal to 0. And I described mathematically exactly where this comes from the exponential before. But here I'm going to go into a little bit more depth. Because this thing only has a value at t equals 0, what happens is that if you integrate from minus infinity to infinity of this delta function by itself, you get 1. And if you integrate from this with the function f of t and let's say this is t minus a, then what happens is it's going to be 0 everywhere when you multiply these two together, and then when you get to the point where t is equal to a, that's when you're going to get f of a, which is a non-zero solution. So we know from before that the delta function of t minus t prime is just defined to be 1 over 2 pi times this integral from minus infinity to infinity of e to the I omega t minus t prime d omega. The way this works is basically that you're going to cover all these different values of omega. And this e I omega term, as you know, is basically just cosine of something plus I times the sine of that something. And whenever t and t prime are different from each other, then what happens is we end up with these periodic functions which will cancel out as you integrate. So you're going to get the same value at different points when you integrate over a period, and therefore you're going to get 0. However, if t is equal to t prime, then the argument of this exponential is 0, which means that it's no longer a periodic function. It's basically going to just be integrating d omega from minus infinity to infinity, which is 0, or sorry, which is infinity. And so it's like this function becomes infinite at that particular point. So if you want to graph this thing, if this is t, and this point happens to be t prime, then the function literally looks like it's 0 everywhere, and then there's a huge spike at just that point, and then it goes back to being 0. So this is how the delta function actually works. It just gives you an infinity at exactly the place where you happen to need it. Next, I want to talk about some properties of the Fourier transforms. The first property is differentiation, and that is that if you take the Fourier transform of the derivative of a function, then this is equal to I omega times the Fourier transform of the function. In other words, by taking the derivative of the function, it's just adding an I omega into it. Another thing is if you take the second derivative of the function and you take the Fourier transform of that, then it's like adding minus omega squared and multiplying that by the Fourier transform of the function. Now, this is pretty convenient for us because, first off, it makes it incredibly easy to do derivatives, but we also take advantage of this in numerical methods in order to do what we call spectral methods, where if you want to take the derivative of a function, what you can do is, instead of trying to calculate it using what we call finite differencing, where you would actually try to find the difference between the function at two different points and how it changes, just like you learned in intro calculus. What you do with the spectral methods is that in order to find this derivative, we would just simply take the Fourier transform of the function to find the Fourier transform of f of omega, and then we just multiply it by I omega, and then we just do an inverse transform. So in that sense, f prime of t is equal to taking the Fourier transform of the Fourier transform of I omega. So in other words, we take the transform, we find the f of omega, we multiply by I omega, and then just take the Fourier transform of that, and we have the derivative. The advantage is that this derivative is much more accurate than anything we can get through finite differencing. Another thing we do, we do integration. And for integrals, if you have the integral of a function, say f of s ds, and you take the Fourier transform of it, that is the same thing as 1 over I omega times the Fourier transform plus 2 pi c delta omega. In this case, you could see that the integral just looks like the opposite of the derivative, where we're dividing by I omega instead of multiplying. And then you have this delta function that naturally crops up. This c here is just the integration constant, so that's not really anything special. We can also scale our results with the Fourier transform. And that's where if you had f of at, where a is a constant, and you take the Fourier transform of it, then that's the same thing as 1 over a times the Fourier transform of omega over a, f of omega over a. And so this allows you to how you calculate these scales. We also do translations, which are where you would have f of t plus a. In other words, you're shifting your solution. You do the Fourier transform of it, and it's the same thing as having e to the I a omega times f twiddle of omega. And then, of course, if the exponential multiplication is where we might take the Fourier transform of e to the alpha t times f of t, and that will come out as just the Fourier transform of omega plus I alpha. In other words, it's like we shifted the Fourier transform itself. So these are all just very useful things that we can do. Now the next thing I want to move on to are talking about symmetry. So for example, let's suppose that we have a function and it has an even symmetry. So f of t is equal to f of minus t. Then when we take a Fourier transform, f of omega is equal to 1 over square root of 2 pi times the integral from minus infinity to infinity of f of t e to the minus I omega t dt. So what's happening here is we know that f of t has an even symmetry, and we're still using this exponential thing. So what we can do is we can actually take this integral and we can break it up into two parts. So if we take, and I'm actually using a different method that's in the book, but you can also read what they do in the book as well. I can think of this as the integral from 0 to infinity of f of t times e to the minus I omega t dt, plus the integral from minus infinity to 0 of f of t e to the minus I omega t dt. So I'm just took that integral and just broke it into two parts. So that is equivalent to me saying I have the constant 1 over square root of 2 pi, and I have my integral from 0 to infinity. And I'm going to take the first one and I'm just going to keep it as is, e to the minus I omega t dt. Now the second integral, I'm going to manipulate this a little bit. The first thing I'm going to do is flip the limits. Instead of going from minus infinity to 0, I'm going to have it go from 0 to minus infinity. And then I'm going to flip the sign of t again in order to account for that. So the new limit on this thing is actually going to go from 0 to infinity. And when I do that, my f of t, whether it's f of t or f of negative t, doesn't matter. It's the same thing because of the symmetry. But what happens is when I flip my definition of t and I made t into negative t, when I did that, then the exponential term became e to the plus I omega t. And then with the dt, what happened was I flipped the sign twice. So I flipped it once when I moved my limit from minus infinity to 0 to 0 to minus infinity, and I flipped it again when I made t go to minus t. So the net result is that dt is the same. And so now you can see I've got these two equations for integrals. They're both being integrated over the exact same limits from 0 to infinity, and they both have the f of t in there. The only difference is I have a negative exponential in one and a positive exponential in the other. So I can actually take those two terms and I can combine them together. So I have an integral from 0 to infinity, f of t, and now when I have an e to the plus I omega t and an e to the minus I omega t, that's a cosine. It's actually a 2 cosine. So I have this times 2 cosine of omega t, and then I have my dt as before. So this integral becomes the square root of 2 over pi, times my integral from 0 to infinity, f of t cosine omega t dt. And so this is a cosine transform as opposed to a sine transform or an exponential transform. And you could do the exact same thing for odd functions. So for an odd function, let's say I had f of omega equal to, or sorry, before I get to the odd transforms, I want to show you something else. Like assuming that my Fourier transform is also even, then that should actually give me the exact same type of cosine transform where I'm going to end up with the same thing, where this is just going to be the Fourier transform f of omega cosine omega t d omega. And so here you could see that the inverse transform is also a cosine transform. And so what happens is having an even function basically means that you're going to have the cosine transform for both the transform and the inverse transform, but it also means that you're going to have the same symmetry in both the transform and the original function. So if f of t of omega is even, then this becomes even. And this makes a lot of sense because if the f of omega was not even, then it wouldn't be a cosine transform. All right. The last thing on as far as Fourier transform before we get into other integral transforms, we're talking about how do we deal with transforms in higher dimensions. So what if you're not just doing a one-dimensional transform? What if it's three-dimensional? In this case, what you can do is instead of just having f of transform of k, I've got kx, ky, and kz. And so this is equal to 1 over 2 pi to the 3/2. And so what happened here was, instead of having just 1 over square root of 2 pi, we've actually got 3 of them. And we have 3 integrals instead of 1. And you have your f of x, y, and z. And then you have different exponentials for each one. So e to the minus I kx, x, e to the minus I ky times y, and e to the minus I kz, z, and you're integrating over dx, dy, dz. And so that would be the Fourier transform. For the inverse transform, it's going to basically be the same thing. So for the inverse transform, we have the same coefficient in front, because again, we're basically doing 3 of everything. You have 3 integrals. You have your inverse transform of kx, ky, kz, and then you have your exponentials, e to the I kx, x, e to the I ky, y, e to the I kz, z, d kx, dky, dkz. So it's very simple. Now you might ask the question, well, what happens if you're in spherical coordinates? Well, in spherical coordinates, f of k would be equal to 1 over, where k here is written as a vector in 3 dimensions, 1 over 2 pi, so 3/2, times the integral of f of the vector r, e to the minus I vector k dot vector r, integrated over the value. And it looks a lot simpler, but you know there's a lot more involved in it, because this integral is equal to r squared sine theta d dr d theta d phi, and also the k dot r term is equal to k r times the cosine of the angle between them. Now you also can have the inverse transform, which is 1 over 2 pi to the 3/2 integral f twiddle of k e to the I k dot r d cubed k. And the delta function can also be rewritten as 1 over 2 pi cubed times this integral of the exponential I k dot r d cubed k. And so you can see everything that we could do in one dimension, we can do in as many dimensions as we need to. All right, so the last thing I wanted to do is talk about other transforms, because this chapter is about integral transforms, not necessarily the Fourier transform. So the first one is called a Laplace transform. Laplace transforms are probably the most common transforms outside of Fourier transforms. And the basic idea here is that the transform is from a function that doesn't have a Fourier transform. And it may not have a Fourier transform because it doesn't repeat, or even if as you go out to infinity, there's not a repetition in the function. And so in this case, Laplace transforms are typically calculated from 0 to infinity of f of t being the original function, and then e to the minus st dt, where s could be complex. Doesn't necessarily have to be complex, but it can be complex. And the inverse transform, in this case, has to deal with the Heaviside step function, where h of t is the Heaviside step function. It's equal to 1 if t is greater than 0, and it's equal to 0 when t is less than 0. And so it is equal to 1 over 2 pi I times the integral over some area of the transform times e st dt. Then we have this thing called a Hankel transform. And a Hankel transform, like you could see that the Fourier transform used an e to the I term, like an exponential complex term. And the Laplace transform just use a regular exponential term. What the Hankel transform does is it actually uses Bessel functions. And so you could see here, the transform is equal to the integral from 0 to infinity of f of x times the Bessel function kx times x dx. And the inverse transform for the Hankel function is equal to the integral from 0 to infinity of the transform times another Bessel function, where you could see that this is very similar. So you got the transform and the inverse transform again. Now the next one is called a Mellin transform. And it has the form where the transform is, the argument of the transform is actually a complex number, z. And so you can see if you integrate from 0 to infinity, the function f of t as usual, but now you have a term t to the z minus 1 dt. And the transform is going to be the integral, 1 over 2 pi I times the integral from minus I infinity to plus I infinity of t to the minus z, this transform of z dz. And so you could see that with the Mellin transform, it's very unusual. This is a z, not a 2, in case anybody's wondering, in that it's basically not using an exponential of any kind or a Bessel function. It basically just uses this t to some number. And so in general, for these transforms, they all basically follow the same model, where the transform is essentially the integral over some range of some function of the two variables that you're transforming to or from, and then the function itself that you're transforming. And so all these different transforms follow that same series. So in general, you're going to be using the same transformation. You're going to be using the Fourier series transformation for most part. Occasionally, you use the Laplace transformation, and there's really not going to be a whole lot else but outside of that you may have to use at this level. Now, I also want to make sure you guys do have the next assignment that's due. And so these problems are going to be due after spring break on the 18th of March. And I picked these from chapter 13 to give you some variety as to what kind of things you might want to, we can actually do with this. So it's 13.1, 13.2, 13.5, 13.7, and 13.13, the lucky one. So that's 13.1, 13.2, 13.5, 13.7, and 13.13. We can discuss this on Wednesday, and I'll remind you guys about exactly which ones are due, and that this is going to be due after spring break. So I guess I'll see you guys Wednesday, and take a look at some of these problems, and before then, and we can discuss where to go. Talk to you later. Bye.